Hi everyone, I'm Rajitha, working as Assistant Professor of Artificial Intelligence and Data Science Department in SNS College of Technology. Today we're going to see about game playing and CSP, and the subtopic is Constraint Satisfaction Problem. The core concept of constraint satisfaction problem, a CSP is described as a problem framed by three key elements: domain, constraints, and variables. The ultimate goal is to find an assignment of values to all variables that satisfy every constraint without violation. The slide emphasizes CSP's importance in AI, where it's commonly used for tasks involving reasoning, decision making, and optimization. For instance, it helps in modeling problems where choices are limited by interdependencies, making it a foundational tool for efficient problem solving in computational intelligence. And the key components of CSP. Variables are the entities or unknowns that require assignments, like placeholders in a puzzle. Domains refers to the finite or infinite set of allowable values for each variables. Think of it as a menu of options. Constraint or the restriction that dictate which combination of values are valid, ensuring the solution is feasible. This structure allows CSP to represent complex problems in a modular way, enabling systematic exploration of solution. Understanding these components is crucial because they form the blueprint for formulating and solving CSPs in AI applications. Examples of CSP. In this scenario, variables represent geographical region on a map. The domain is a limited set of colors such as red, blue, green. To minimize the number needed, the key constraint is that no two adjacent regions can have the same color, preventing visual overlap or confusion. This example demonstrates how CSP can solve graph coloring issues which have broader implication in scheduling or resource allocation. It is a simple yet powerful way to visualize how variables, domains, constraints interact to find a valid coloring assignments. Types of constraints: unary constraint, binary constraint, and global constraint. Unary constraint apply to just one variable, like restricting a variable to a specific value or range. Binary constraint involve two variables, such as ensuring two events don't overlap in time. Global constraint encompass three or more variables, like requiring that all variables in a group sum to a certain value. This classification helps in selecting appropriate solving method, as different types influence the complexity and efficiency of algorithm used in CSP resolution. And the representation of CSP. In this graph, note symbols the variables, while edge connect nodes that have constraint between them, representing the relationship or restriction. For example, in the map coloring problem, regions would be node and border would be edges. This graphical representation aids in understanding the problem structure, identifying densely constrained areas, and applying graph-based algorithm for solving. It transforms an abstract problem into a tangible diagram, which is particularly useful for debugging or optimizing solution in AI system. CSP solving techniques. Backtracking search is a depth first approach that tries assigning values incrementally. Backtracking when a constraint is violated, essentially a smart trial and error method. Forward checking enhance this by proactively removing invalid options from future variables, domains after each assignments, reducing unnecessary exploration. Constraint propagation involve techniques like ARC consistency to iteratively narrow down domains based on constraint, eliminating inconsistencies yearly. These techniques combine to make CSP solving more efficient, especially for problem with large search spaces, by pruning invalid path and focusing on promising solution. And real life application of CSP is this it include scheduling tasks such as timetabling exams to avoid conflict, assigning flight crews without overlaps, or rostering workers to meet shift requirements. Resource allocation examples involve distributing machines in manufacturing or bandwidth in networks. Other application are solving puzzles and map coloring for geographical or political boundary representation. These source CSP versatility in optimizing limited resource under rules, making it invaluable in operation search, logistic and entertainment. And the advantages and challenges is advantage include offers a structured declarative framework for modeling problems, which simplifies formulation and enabling efficient systematic search that can handle combination explosion between that than brute force. However, challenges arise with scalability. Large or highly constrained problem can lead to exponential computation time, making them slow. Real-time application demand optimized algorithm to mitigate this, such as heuristic or parallel processing. Overall, it positions CSP as a balanced tool, effective when paired with advanced techniques to overcome its limitations. And the conclusion is it is widespread use in practical domains, blending theoretical foundation with real-world applicability. The emphasis is on how CSP bridges abstract concept with tangible outcomes, encouraging viewers to appreciate its utility in AI fundamental. It wraps up the presentation by reinforcing key takeaways, preparing the audience for further exploration or questions. Thank you.